Folks, I'm making two video segments on the problem chapter 15. There are some minor changes that I'll make as I go along. Chapter 15, the title of chapter 15 is, let me see for a second, is bearing shaft assembly using analysis connection, of course. It's an assembly. And the geometry that you see is shown here in chapter 15. The bottom of these bearings, the two bearings on the left and right, are clamped, and the shaft is subjected to a load. It says 1,000 pounds here, but I'll make that thing maybe 200 pounds instead. Now the other thing is that it says that the shaft is uniformly subjected to that. That's not a realistic type of loading, because when you say, for example, let's stick to 1,000 pounds for a second. So if it says 1,000 pounds and there are 1,000 nodes on the shaft, including the ones that are inside the bearing, on each node, whether it's on the top, in the bottom, or on the side, a load of 1 pound is applied. Now I can see how you can apply perhaps a load of 1 pound at the top, but it's going to be very difficult to apply a downward load to the points below the shaft at every node worth 1 pound. So what I'm going to do instead is you will make a stand in the middle of the shaft. In the middle of the shaft, I will make a stand and then apply that load, which is either 1,000 or like I said that I'm not going to use 1,000. I'm going to use 200 pounds on that stand. Okay. The other thing is that the first video segment assumes that no planes of symmetry are used. So as it is in the book. So that's what I'm going to do, and I'll make a few comments about unrealistic assumptions made about the shaft as we go along. Then I'm going to, in the second video segment, I'm going to use planar symmetry to reduce this thing into smaller domain. Okay, I'll stick to the dimensions that I have. Let me immediately save this assembly file, save management, save as. Save as on the desktop, a new folder. I'll call it chapter 15. Chapter 15, no symmetry. All right. Okay, let's make the left bearing. So insert, new part in there. Actually, you know what? Why don't I make the shaft first? So let me rename this thing to be shaft and shaft. Okay, let's make it. On a convenient plane, on that vertical plane, I will make a circle. The diameter of the circle is 1 inch. Put it in my shaft section. Exit. And I'm going to pat this thing in both directions. Oops, nothing. A mirror extent in both directions. Now in the book, it said the total length of the shaft is 6. I will make the total length 10 inches, okay? So I'll make 5 in each direction, and there's our shaft. Except that I would like to make a stand right in the middle, so on that horizontal plane, I will make a sketch. Right, I'll make a sketch, perhaps a circle. Why don't I make it, diameter, instead of 1, I will make diameter 0.75. Okay, exit. And then pad it. Not that high, perhaps 1 inch. Let's see what happens. Yeah, and I will apply the load that the book says 1,000, but I told you I was going to use 200 on that shaft. This entire assembly is made of aluminum, so I thought 1,000 was going to be a large deflection if you use aluminum. So Alright, good. So now we're going to immediately save this and insert our left bearing. Okay, so insert a new part, say no, right click properties, left bearing, left bearing, and left bearing. Okay, let's make it. Double click on this. On a convenient plane, on that plane I will sketch. Okay, well, first of all, let's project that circle, because the size of the the size of the hole is the same as the size of the shaft, and then we complete the rest of the bearing here. Something like this, perhaps. I'm gonna clean it up in a minute. Okay, so according to the drawing in the book, the diameter here, radius is 1, or diameter is 2. Okay, and let's see now. This height is 2. Okay, and that's pretty much it. I'm pretty sure these two are concentric, but yeah, they must be concentric. So exit, and then we pad it by a thickness of, I don't know, I think it looks like in the drawing in the book, it looks like the thickness is 1. It may even be 0.5, I'm not sure. Okay, good. That's fine. Now I'm going to make an identical bearing on that side. Of course, I can do a copy paste of this, or I can insert, or I can save this, save the whole thing, distinct component, which is going to be identical to that. But I will make it actually. So let me make it. So insert, new part, say no, right click, right bearing, properties, right bearing, and right bearing. Okay, let's make it. Double click on a convenient plane. On that side plane, I will sketch. I repeat the same process. So project that circle. Okay, and then draw the rest of it. Now the rest of it is exactly like this guy. So maybe what I should have done, instead of projecting that circle, I should have projected that entire face. Okay, so let me undo this. Okay, so project instead that entire face. Did I do it? Right there. So exit, and then pad it in the opposite direction. Thickness is 1. Okay, good. Save everything. Go to the assembly level and save everything. Let's make the entire assembly made out of aluminum, with default material properties. So apply material, metal, aluminum on that assembly, and then close it. Okay. So everything is made. The only difference between what I have here and what's in the book is that the length of this shaft is larger, and also there is no stand in the book, so the load is applied on the entire shaft, which is not realistic. Alright, now we're going to go to generative structure analysis. Catia sees 3 parts. Immediately it meshes each of them. and it's you can go ahead and change the size of different elements. For example, the one in the shaft is definitely too big, so let me go ahead and change this thing to perhaps I don't know, 0.2 to say, and I don't want parabolic, because parabolic will take a long time. For video, I'm not going to do that. So everything is linear. Let me change this thing to linear, but the size of the bearings I'm not going to change. Okay, good. And if you want to see the mesh, let me move these things out of the way. Okay, if you want to see the mesh, you go to nodes and elements, right click, mesh visualization, and there we are. Okay, deactivate the mesh and move on with the rest of the problem. Okay, the bottom, notice that there is a plane of symmetry here. It could be depending on what's done at the end. It's really not possible to say how many planes of symmetry you have until you decide on the load and restraint. But for now, let's not worry about that. In this video segment, I'm not going to make any planes of symmetry anyways. So the bottom of these two are clamped, and there's a total load. There's a total load, not pressure, total load of 200 pounds in the direction Z. So this is 0 in the direction Z. Yep, see that? Okay, very good. Now, let me remind you that if I run the problem, this will collapse. It will crash because the shaft is not does not have any stiffness in any direction. Basically, these parts do not see each other, and they're going to go through each other like butter. The first thing I'm going to do, though, is I'm going to save this analysis file. Before I run, I'm going to save the analysis file, and then I'm going to run it, and we'll see that it will actually fall apart. It will actually crash. Crash meaning that it will not run. Okay, you can see that. And if you want to see what happened, you can ask Catia to show you the deflection, and you can animate it, and you can see that the shaft does not see the bearing, and the other way around. So we have to create connections and somehow decide on how the connections are made of. Okay, so let's deactivate this plot. We'll deactivate that. Okay, so the connections, we're going to make two of them. Let's see now, a connection between the surface of the shaft, and for the second component, hide the shaft and select the surface of the bearing. And I'm going to repeat this on the other side. Okay, another connection. Let me actually, this connection, let me call this thing right-click properties. Okay, let me call this thing left bearing connection. Left bearing connection. Okay. Left bearing connection. Okay. Alright. Good. And I'm going to do another one. First component, surface of the hole. Second component, surface of the shaft, which is in hiding. I'm going to bring this in the front also. And I'm going to call this thing right bearing connection. Okay, good. Alright. Now, we know that these two cannot penetrate each other, so right away we're going to call these things, we're going to make them contact connection under the face-to-face connection right here, contact. This is going to become contact, and the other one is also contact. And you can see the icons are placed here to signify the fact that contact connection has been established. So the bearing, the shaft can no longer penetrate on either the bearing, but that does not solve our problem, as you'll see in a minute. Let's try to run it and see that it miserably fails. Let us plot the deformation and animate it. If you can't see it, that's because the scale was reset already in the previous failure. So I'm going to say default, and I'm going to animate it. You can see that the shaft no longer penetrates the bearing, but it can slide along it because there's nothing that restrains it. Now this is where one thing I don't like about how it was done in the book. In order to fix the issue, what I did, I clamped this end of the shaft, but that's ridiculous because that's kind of meaningless. What I do instead, let me assume that the edge of the shaft and the edge of this hole are welded together. Okay? Welded together. Welded means glued together or tied together or fastened together. Okay, so what we're going to do is we're going to create another connection, and I'm going to call this thing left bearing I'll call it tied. Okay, tied to the shaft. To shaft. Okay, so for the first component, let me hide this thing for a second. For the first component, I'm going to select the circular periphery of the shaft of the bearing, and for the second component, I select the circular periphery of the shaft. Let me bring it in the front so that there's no mistake here. I'm going to hide the bearing now and select the circular cross section, the periphery of the shaft. Okay, good. So here is the third connection that we created, and let me bring this shaft in front of you so that you can see it. Although we don't need it, we can select it from the tree. We're going to make this thing fasten. Fasten is right here, right next to contact. It is also fasten. So we're going to make that thing fasten. Notice there's a fastener sign placed here. If you look closer, fastener sign, which means the edge of the shaft and the edge of the hole are fastened together, tied together, glued together, etc. Now, this will not only stop making this thing go in the horizontal direction, but also couples with the bearing itself. So this time it will run, and let's find out how it's going to work out. All right, good. So look at the deformation. If you can't see much deflection here because we reset the bearing, remember we reset the bearing here, stop that, go and reset it again to default value, and there we are. You can see that. Okay, you can see that. Animate it. So the bottom of these bearings are clamped. The shaft, that platform on the shaft is loaded. These two are tied together, welded, whatever, and therefore it looks like that. Now, if you look at the other side, however, you can see the shaft will stick out of that hole because these are not tied together. Now, if that is the case, there is one plane of symmetry, and that one plane of symmetry, if this is our loading, the one plane of symmetry that we're dealing with is YZ. However, if I tied these two together, exactly like I did on the left side, then you'll have two planes of symmetry. Okay, so I will stop this video segment right here because my plan is to go and cut this thing first into I'll cut it into if the connection is like this, there's really not much choice. I cannot use two planes of symmetry. I will use only one, and we just solve the problem like that. Okay. So let me go ahead here. First of all, save everything. And then what I want to do is I want to create, because of my second video segment, I want to have the assembly in a separate folder so that any changes that I make there will not change what I did in the present folder. So what I'm going to do is I'm going to say File, Save Management. This product, the product here, Save As. Not in that folder. I'm going to go to the desktop. I'm going to create a new folder. I'm going to call it Chapter 15. Chapter 15, One Plane of Symmetry. One plane of symmetry. And say propagate directory so that it takes the assembly and the parts and put them both in that same folder. Let's go and check it here. So I have a folder. This was no plane of symmetry, which we just did. Analysis file is also in it. This one does not have any analysis file because all it did was to put the product, and because of the propagate directory, it also puts the parts there. So I'm going to stop the video segment here, and we're going to do the one with the plane of symmetry in a different one, because I don't want these to be too long in case things